Okay. So hello again, and hello for everyone who sees it in recording. Now, today we're going to start to apply our knowledge from last lecture and continue to apply our knowledge from previous classes. So today we study inverse kinematics. This arguably might be the first material that you haven't seen at all, as in previous lectures, like on Jacobians, frame transformations, was a mix of linear algebra and theoretical mechanics. So there was a small chance that you have seen some of it here and there, and we mostly were putting things together for you, right? But here, inverse kinematics, I think that is almost definitely new information, in my imagination at least. So inverse kinematics is a problem of trying to find joint coordinates, joint parameters, like, joint, for example, coordinates, velocities, accelerations that produce desired motion in Cartesian space. That will be best in, seen an explanation, but that is the idea, right? To put it more concretely, imagine you have a KUKA robot. I tell you, please make sure its end effector points at this particular point in space. Like, I want to touch a what do you call it? Blackboard, right corner. Just touch it with your KUKA robot, and you have to input joint coordinates for the KUKA robot. Where do you get those coordinates? Well, this is what inverse kinematics is all about. Okay, now let us begin. So given a point, let's say end effector, but this is true for any point. This, like, doesn't have to be end effector, but end effector is what we typically work with. Given a point, position of the point described by a vector, we can find velocity of this vector, okay? By differentiating. That is what we did last time. And, seems to be a, easy, straightforward procedure. Just to remind you, this is just differentiation of a function, where you have a derivative with respect to parameter, and then the derivative of the parameter. In Russian would be производные сложной функции. Okay. For simplicity, let us introduce some notation. It will be extremely useful for this lecture. We denote Jacobian as G. It is dr dq is Jacobian. We denote velocity as v. It is r dot. So what we get is the same expression here becomes this guy, right? V, so velocity, is equal to Jacobian times joint velocities. Let me just spend a minute reminding you, this is Cartesian velocity. This is joint velocity. This is Jacobian, okay? Those terms are just nice to remember. They're useful. I use the word joint coordinates because we have been talking about joints. And for something like a KUKA robot, that is the correct terminology, right? But for some other robots, let's say for a walking robot or a car, that wouldn't make a lot of sense. So sometimes we instead use the word generalized velocities or generalized coordinates. Generalized implies that you use just Lagrangian notion of generalized velocities or generalized coordinates, which is a minimum set of parameters that completely defines position of the system of rigid bodies. And joint coordinates kind of implies that you describe how joints are oriented. For KUKA, both are the same. For walking robot, you have 6 coordinates of the rigid body plus joint coordinates. For a quadrotor, you don't have any joint coordinates, you just have coordinates of the rigid body. That is just for terminology. You don't have to memorize any of this. It is clear from the context usually. But it's nice to remember the words that we are using here. And now you can maybe see some of the justification why I'm keeping English for you as a language of instruction. We have to get used to those terminologies. Okay. Good. Now, if we have this expression, can we find a least residual solution for this problem? Least residual means smaller the discrepancy between the left and the right. Can we? Well, of course we can, right? The solution would be J pseudo-inverse times V. We derived this formula last time using, I remember the first 2 slides, using the idea of let us define the residual, we'll define the norm of the residual, we'll minimize it. It is the same as squaring the norm. Then we open the brackets, take partial derivative of what was in the brackets, set it to 0, and we get expression which we defined as pseudo-inverse. Okay, this was a process from last time. If for some of you this process sounds mysterious, unfamiliar, and so on, please revisit last lecture. Understanding how least squares is derived is immensely important. It is not for like FYI, it is just practical knowledge. So I suggest revisit last lecture. It will be good for you. Okay, so yeah, on GitHub, like this lecture and the next one. I don't know if the one. Well, anyway, all the lectures will be updated on the GitHub today. Thank you, Ivan, for reminding me. Thank you. So this expression here, expression 5, gives us one solution. And but is this all? Is this all that all joint coordinates that solves this equation? Can't we find something else other than v q star that solves the original equation? Well, the answer is yes, of course. We have other things that solve the original equation. All solutions can be found in this way, where expression 6, where here J inverse V is a pseudo-inverse solution. So it is a least residual solution. In other words, this is a row space solution. And this is a null space solution. N here is null space of JK, of Jacobian. And Z are null space coordinates, just some numbers. So for any Z, you would produce a new Q dot, which would be solving the original equation. Okay, so let me reiterate, this is important. This is one number, it is a row space solution. Only one vector here can solve this problem. Here though, you can put any Z, just generate a new Z, put it there, it will provide you a new Q dot, which would solve this problem. Okay, that is, as long as this least residual solution provides you zero residual solution. Okay, as long as it provides you zero residual solution, then it would this would provide you also zero residual solutions. If this somehow if this somehow provides you a residual that is not 0, this would provide you the same residual as 5. So the point of 6 is that it does not increase residual. So if 5 had a 0 residual, it will be 0 here in 6. If 5 had a residual more than the 0, 6 would have residual the same as 5. Okay, good. Is there any questions about what we just did? Is there any questions?
No.
Okay, thank you. All right, so what we see here is just like one way of doing it. Another way of doing it, expressing this expression here, is like this. Expression 7. Expression 7 represents what is, in my private opinion, more popular in the literature, but might be more confusing, I think. But more popular, and for a good reason. You will see in this lecture, in just a few slides, why expression 7 is extremely, extremely useful. Okay. Just in a few slides. Okay, what does expression 7 say? It says, okay, you have a row space solution, J pseudo-inverse V, plus projection onto the null space of J times any Q dot. Okay. So let's look at it again. This is a row space solution. So this provides us exact solution to the problem if there exists exact solution. If there doesn't exist, it provides us smallest residual. What this does, it takes as input any Q dot whatsoever. And here it multiplies it by a projector. This is a null space projector onto null space of JK. So you get JK is a, just projector matrix exists, right? It projects stuff into the null. JK, yeah, is a matrix, and this whole thing, I means J pseudo-inverse J, projects stuff in the null space of this matrix. Remember properties of the projectors. Projectors are n by n square matrices. So this is n by n square matrix. This guy in particular, let me show it, would have been a row space projector. So this would have been a row space projector. And if you want to make a projector onto the orthogonal complement, you get I minus projector to the original subspace, right? So I minus projector to the row space gives us null space. I tell it to you because we will see it today 2 or 3 more times. So if you have a projector somewhere, I minus this projector will give you another projector, now to the orthogonal complement. Okay, good. Okay, good. So what does this expression do? It operates with Cartesian inputs here and with joint velocities here, which is kind of bizarre. But here also it was Cartesian inputs and some new coordinates here. So this was also bizarre. All of this is strange. But as a plus sign, what you can say is here, at least, this is understandable. This Q dot is something that we have seen before. It's just any joint velocity whatsoever. And you say, I will cut it up, get only null space component. Everything else will go away. And here I add a row space solution and I get the solution. So somehow this makes sense. If you think of this as a filter that filters out everything that is not a solution, this starts to make sense, I think. All right, so expression 7, this is how it works. Let me know if you have any questions about it. And further in the lecture too, you like just anytime, this is a complicated stuff. So. Okay, if not now, like anytime further in the lecture, stop me and we'll discuss this. This, I think, is a little bit not trivial. Like, it doesn't sound. This, I think, at least corresponds somehow to maybe a linear algebra class. Maybe, I don't know. But this, I'm pretty sure, doesn't. So, what do I know about the linear algebra classes, right? Okay. Okay. So you have seen two ways to express all solutions to inverse velocity problem. So velocity problem or inverse velocity problem is a type of inverse kinematics where you ask about velocities. All right. Now, next. Let us solve something that I called optimal velocity problem. That is not a terminology from literature that I picked up. I just wanted to point out it is slightly different, but don't take it too seriously, the optimal part. Let us find, let us find the closest joint velocity to Q0 that solves the velocity problem v equals to j q dot. Yeah, let us find the closest velocity to Q0 that solves the velocity problem v k equals to j q dot. So what we're minimizing here is the distance between the q dots that we'll find and q dot 0, subject to constraints. Constraints is vk should be equal to jk times q dot. Okay. How do we solve this guy? Well, the way to solve it is first we'll find all solutions as before. And what we can see here is, again, row space solution, null space solution. I used this notation here. Sounds good. Okay. Now we have new coordinates that parameterize this equation. You remember when we talked about kinematics, we said that Euler angles, for example, parameterize matrices, or joint angles parameterize matrices. So here we say Z parameterizes this equation. Okay. So what changes here in this equation is Z. This is fixed. So this is fixed. Only Z changes. So those are parameters. We can take this whole thing and substitute it into here. What we get is this equation. So we want to minimize j to the inverse v plus nz minus q0. We get this kind of stuff. Now, from there, we can try to solve it. It has an analytical solution. First, we introduce notation. I will call this part C. So what we get is now much simpler, nz plus c. Let us now consider its derivative. So first, minimum of this function is the same as the minimum of this function. Derivative of this guy is given here. I mean, I have to take derivative of this guy with respect to z and set it to 0. Here is how derivative looks. It is 2z n transpose plus 2c n equals to 0. How did I get it? I mean, you can see if I open the brackets here, I would have z n transpose n z, right? This is how we got this first part. When we differentiated this with respect to z, we get 2z and n transposed. And then I would have two identical scalars. One was c transposed nz, and another was z transpose n transpose c. So two identical scalars. they're scalars, so they cannot be like transposed with respect to each other. And we took derivative, and that's how we got this guy. C times C derivative with respect to Z is 0. So that's what we got. Y minimum is the same for matrix A and A transpose times A. I don't get the question. Why the minimum is this?
I just, I meant the line when we consider NZ plus C and then go from it to the, yes, here.
Okay, so that is actually relatively simple. Let me just justify it in a second. So what this does here, let's say we want to find the minimum of D norm, right? We want to find the norm mean. Okay, what this does is it minimizes the norm. Norm is, on the other hand, is square root of D transpose D, right? So it is the same as trying to find a minimum of square root of D transpose D, okay? Oh, sorry, yeah, that is exact. So far, we didn't change anything. We just explained what the norm means. But the norm of a square root of a number for a positive number, right, is the same as the norm of, the minimum of the number itself. Like those norms coincide. You cannot find the minimum of a square root, which does not at the same time is the minimum of the number, because this, you can kind of say that square root is an always increasing function. So it you remember the graph of the square root, right? It kind of goes like, I don't know if I want to draw here because it would be horror, but you remember the graph of a square root. It always increases. So if you want to find its minimum, you have to find the minimum of the original function. And so we say that this is the same as saying D transpose T set to minimum. And this is exactly what we did here, expression 12. Does this make sense, Ivan?
Yes, absolutely.
Oh, thank you.
Thank you.
Great. This is one of those tricks which is crucial for a lot of math we do in optimization. There are a lot of them, but this is one of them, and it's good, it's good to just keep it in your tool set. N transpose N can be a singular matrix. How can we inverse it? Ilya asks. So, in general, if it was just any matrix, let's say it was just any matrix, it could have been singular. It could have been singular. Absolutely. And then we couldn't inverse it. What it would mean was that our parameterization, so our Z parameters, were not independent. That's indeed true. And that is something that you have to keep in mind when you look at the previous lecture slides on how we derive the pseudo-inverse solution, so least square solution. If you want, you can ask yourself, can we do it somehow better? And maybe then you would find like answers to deeper questions that you're asking. What you ask is quite a, not the simplest questions. Let me put it this way. All right. In our case, so N cannot be singular. N transpose N cannot be singular. In fact, here I'm making it a little bit more complicated than it has to be. I can prove to you that this guy, N transpose N, is identity. I can prove it to you by saying that N, as a basis in the null space, we could always choose orthonormal basis. Okay? And orthonormal matrices, one of the key points, as we discussed, I think, I don't remember which lecture it was, but we discussed it, I remember. Orthonormal matrices have a property that the matrix times itself transposed if it is inner product. So we have inner products of the columns. So if n is orthonormal, n transpose n is identity. That is a property of orthonormal matrices, is a definition of those matrices. So as long as n is orthonormal, this guy here is identity, not just differentiable, it is identity matrix. But it doesn't. We don't have to make it orthonormal. We can just make it full rank, full column rank. And as long as this full column rank, again, n transpose n will always be full rank. Can we prove it? Yes, we can. We are not going to prove it now, but just note it for yourself. If it is full column rank, you can always prove that n transpose n is full rank. And if you want to prove it, take a piece of paper and go with it. Orthonormal bases cannot be singular in any dimensions. If you want, you can try to demonstrate me at least one that is singular, or somehow else prove me existence of singular orthonormal bases. I would say that being singular contradicts the definition of being orthonormal. Okay, for basis. Being singular actually contradicts the definition of being a basis. If you want, you can see how we define the basis. I'm not saying that you're like terribly wrong or anything. I'm just saying that basis is, I think, defined as a set of linearly independent vectors that span the whole subspace. And a linearly independent implies that the columns of the matrix that they are creating would have to be linearly independent, which implies full column rank. So this implies that the matrix would be full rank. But I like those doubts. I think doubts like this about singularity is exactly what we need to move forward. So good. Thank you, Ilya. All right. So let me move on. If there are any other questions, just talk. And you can write in the chat. You can also just talk on, it's fine. Okay. All right. Now, so we get this equation, and from there we just get z by, inverting. You can see how we can get from 14 to 15, right? We put this to the left with a minus sign, 2 goes away. You have to transpose the whole thing because right now s and z are on the left. You have to put them on the right, so you transpose it. That's how you got here transpose. And that is how we get 15. Okay. Now, knowing that this is what we had originally, and this is z, we can now put one into another, and we get this equation, 16. Here you can clearly recognize, again, a row space solution. But here, on the other hand, I'm jumping a little bit ahead, but let me note, this is pseudo-inverse of n. This is pseudo-inverse of n, okay? Which is, if it is a orthonormal matrix, it is the same as n transposed. And why? Because if it is orthonormal matrix, as I said before, this is identity. But we don't have to assume it is orthonormal, right? For our derivations. This is pseudo-inverse. And matrix times its own pseudo-inverse gives us column space projector. Column space projector. So what we see here is a column space projector. I just noted for you, so you kind of recognize what's going on. But it's okay. It's not like super important. Okay. Okay. Just keep in mind on those blocks of matrices to see what kind of projector you get. Could you specify with respect to which argument we are trying to minimize the equation? The original equation here was minimized with respect to z. Before that, we tried to minimize with respect to q, but we found that q is parameterized with respect to z, so we minimize it with respect to z. Hope I answered this question. Okay, good. Good. So expression 16 is what we got, right? C is still giving us this expression. So we somehow would want to put this whole thing into there, right? We want to put this guy here. So let us do that. So here we put C in, and we have this long expression. I'll open the brackets, and we would get here identity, here this guy. All of it will be in front of J pseudo-inverse V. And here we'll have again this guy in front of Q0. So what we have here is what is in front of Q0. What we have here is what is in front of G pseudo-inverse V. Now, I will show you maybe for the first time a real power of thinking about projectors. And last lecture, there is a real power to it, and it wasn't just like for, you know, to make cool tricks, right? It was to do real mathematics. So let me show you for the first time what it does. So first, as I said, this was a column space projector, right? But it was a column space projector to n, right? Again, let me remind you, how did I know it was a column space projector? Well, this is a pseudo-inverse. This is n, no, as a matrix, right? So n and pseudo-inverse together gives us column space projector onto n. I understand it is hard to memorize those things. Yeah, we'll get those slides from the last lecture to GitHub. Go through them. I will get them right now, right after this lecture. Go through them. Try to see if you can somehow memorize or whatever those things. I mean, this is not very hard. I promise you. It is. There are two things you have to memorize, like P, matrix pseudo-inverse, column space projector, matrix pseudo-inverse matrix, row space projector. That's it. And those make sense. If you think about them, they make sense. So you can derive it in your head. Okay. So I know this is a column space projector from just looking at it. But column space of what? Of n. N is a null space basis. So this column space projector projects us into the columns of n, so into the null space. So this guy, 19, gives us projector onto the null space of J, okay? Because n is a null space of J. And this is a projector onto the columns of n, so to the null space of J. So n is an, right? The column space projector for n, hence it is a null space projector for J. Okay, this is something. So this is a null space projector for J. Next, now we can go faster. This again is a null space projector for J. And as such, because it is the same thing as before, and I minus any projector gives us a projector to the orthogonal complement. Projector to the orthogonal complement. So instead of being a null space projector, now I minus this projector gives us a row space projector. Row space projector. That is why R here. So this is a row space projector. A row space is orthogonal complement to the null space. So this is somehow a row space projector. Okay. Looking at it, it is a little bit hard to see how this is a row space projector, right? Like you look at it, you say, this is a mess of matrices. This is just like a forest of lines. Sounds good, but you know, if we remember material from this previous lecture, we can figure out it as a row space projector. And I think this is powerful. Now, is it useful as well? Well, it is useful, indeed. It is useful. We will see it in just a second. But now let me rewrite it. So we get Q dot equals to a row space projector here times J pseudo inverse K plus null space projector times Q dot. Okay, good. Now let me show you how useful it is. We can, so we have this expression. This is what we got. We know that pseudo inverse lies in the columns, lies in the row space. Here is a mistake. In the row space. In the row space. Let me write it here. Pseudo inverse lies in the row space. How do we know? Remember last lecture we actually proved it by showing how through SVD decomposition pseudo inverse is computed. Pseudo inverse was given as I don't know if you remember. Let me just write it here. So pseudo inverse of let's say J. Let me write it like pinf of J would be equal to, I hope I'm not making mistakes, row space times inverse of sigma times column space transposed. So pseudo inverse of J would be equal to row space times inverse of singular values times column space transposed. What is important for us is that the output is a row space. So the output lies in the columns of the row space. Okay, so this is just comes from understanding how pseudo inverse is computed. Now, what we are trying to do here, right, is project pseudo inverse, which is already in the row space, onto the row space. And projecting something that lies in the row space into the row space returns you your output. We talked about it very briefly, but the foundational property of a projector is that it cuts everything that does not belong to the subspace and leaves intact everything that does belong to the subspace. Okay, so everything that does belong to the subspace, it leaves intact. That is a foundational property of a pseudo of a projector. Okay. Now, notice what we obtained here. We obtained here is the fact that this expression does not need PR. So we can go to the expression 23. But before we go to 23, let me also just do one more. Remember, this was null space projector. Pn is a null space projector. We remember how null space projectors are working. This is a formula. How do we get this formula? Well, this you can just memorize is a row space projector. J pseudo inverse J, and I minus row space projector gives us null space projector. So this is the formula that we get. We replaced this guy with 0 and this guy with this guy. Now, let me just ask you to spend a second admiring formula 23 and understanding how difficult it is to see how we get from expression 18. Look at this forest of n, right? To expression 23, where we have very clean thing here. Remember, we got rid of this whole thing, like all of this we got rid of. How? Well, by observing that somehow this expression is a row space projector, and this indeed lies in the row space. So this is completely unnecessary. This is completely unnecessary. Okay, and we get this here. How did we get it here? Well, we realized that this guy has to be equal to this guy because both are null space projectors. This is the power of the previous lecture. We can go from one expression to another in this fashion. And, I think I'm confident enough that this was not trivial. And this wouldn't be trivial without knowledge of null subspaces. Okay, so does this make sense to you? How we got to 23? Does this make sense to you?
Symbolically, yes.
Okay. Okay. I understand that we, it requires time, right? Okay. Thank you, Ivan. Good. Now, we can interpret it this way, what we got here. We have the solution is a row space solution plus we want it to be as close as possible to q dot 0. So we project q dot 0 onto the null space, and that is how we get the solution. Project q dot 0 to the null space, add row space, you get the solution. Okay. Project what we wanted to get close to be close to onto the null space, add the row space solution, you get the solution itself. Okay, so this is how you can solve optimal inverse kinematics. And again, I was only calling it optimal because we had this imperative to be as close as possible to Q0. Now, let me show you something interesting. I hope you can keep in mind this formula for a second. So now let me go back and show you this formula here. Fascinating, isn't it? It's the same formula, except here we were saying Q is just any Q whatsoever, just any Q whatsoever, and this will be a solution. So this was the formula for all possible solutions, right? All possible solutions. And somehow, if instead of Q here, we substitute Q0, what we get is one particular solution which happened to be closest to Q0. So this wasn't just a formula for all possible solutions. This was also a formula to the solution that is closest to whatever we input here. So this is the power of this formula. But you can see here, we derived it very easily. We just said, okay, this particular solution, null space solution. That is all we did. It took us no effort whatsoever. Well, here we went through like optimization, parameterization, extremum, substitution, found extremum, solved the least squares, substituted back, look at the expression, substituted back, regrouped, analyzed subspaces, and then finally we got our expression back. So a very different amount of work, but we obtained a very important result. We got the fact that this is a solution to an optimal problem, this optimal solution. And I would recommend you not to shy away from this kind of things. Like try to understand what exactly your formula does. Does it provide you optimal solution? Does it provide you all solutions? What does it do? And to understand that, you have to derive. Even if when someone gives you the formula, look for its derivation, how it's derived. In my practice, like half the time, formulas are not derived as easily, as not derived like in front of you. You have to look for derivation. Sometimes you have to derive it yourself, but don't just stop at looking at the formula, derive it. Like you can see here, 23 and the first formula are exactly the same, but 23 proves us much more than the first one proved. All right. All right. Now, let me just quickly see. We are halfway through the material, so let me make a small break. You think about what we just saw here, because after the break, we'll also have a little bit of an intense session. It's not going to be too intense, but we'll make a short break. You can relax and then we'll go again. Let me just quickly see the time. Okay, so we've finished this part. Now let us go next. Let us now go consider acceleration problem. Acceleration problem. What do you mean by acceleration problem? Well, let's find second derivative of the position of k. What is the second derivative? Well, second derivative, k double dot, is, you remember the first derivative, right? It is dr dq times q dot. Well, we need to take derivative of that with respect to q. So remember, derivative of a product is, a times b. What is the derivative? Derivative of a times b plus derivative of b times a. Well, this is the derivative of q dot times Jacobian. This is the derivative of Jacobian times q dot. So this is how we get this formula. Okay. Let me reiterate. Derivative of q dot times Jacobian, derivative of Jacobian times q dot. Okay, this is how we get it. Good. Now, introducing notation that a k would be r double dot, we get a k equals to jk q double dot, this guy. So this is where we get this part, plus j dot, this is j dot, times q dot. Okay. I hope this is clear. In a sense, if you remember that v is equal to j times q dot, what's the derivative of j times q dot? Well, it's jq double dot plus j dot q dot. So this is somehow, I think, clean, is easy to understand. This might be more confusing because of the big amounts of partial derivatives and stuff. Okay. So least residual solution for this problem can be easily found, because ultimately this problem is exactly the same as the previous one. You have variable times matrix and right-hand side. It's just like you get this thing. Let me put different color. You get this thing. You put it to the right-hand side here, or left-hand side, I guess, in this case, and you get the same as before, the same situation as before. So we get our expression here. Q double dot equals to j pseudo inverse a minus jq. So is quite simple. Quite simple. Do you understand how we got from here? Let me do it. Do you understand how we got from here to here? Okay. So that was simple, right? Now, given this expression, we can again find acceleration closest to q double dot 0, that solves the acceleration problem. And the result would be this. So this is a row space solution, so PINF solution. And this is a projector onto the null space of jk. And that here is your acceleration you're supposed to be closest to. So we can directly import the previous results here, because nothing changes, right? The only difference is that we have now this component. Does it make much difference? No, not really. So in terms of math, this is quite the same. You cannot ignore this component. If you ignore this component, you just get incorrect results. But not ignoring it is actually quite simple. So you just pay attention to your formula. You remember that there are two things here, not just AK, but also JK dot Q dot. And that's it. That is all you need to do additionally. I think when you study theoretical mechanics, for you, the difference between velocity problems and acceleration problems are very big, because there you have to think like, what's the tangential acceleration, what is normal acceleration, what is Coriolis acceleration, what is centrifugal acceleration, etc. Right? All those things. Here, somehow, you don't really get much increase of difficulties with accelerations. You get this component. As far as accelerations are concerned, it is constant. You're not so lucky always. If you were working in the state space, you might have at the same time trying to find AK, and you might have at the same time trying to find Q dot and Q double dot. That is possible to do in state space formulations, maybe, right? But in our second order formulations, you find Q dot, you find Q double dot, you can try to find them independently, and you see both of those boil down to the same kind of like structure. So it's not much more difficult, and that is very good news. That's very good news. So what we did before, we get to for free exploit right now. Okay, hope this is clear. Now, here comes the most difficult part of the lecture. It's not like mathematically much more difficult, but it is conceptually, I think, a little. So what we want to find Q star, such that RK, so position of point K, of Q star is equal to R star. So remember previously we were asking how to find joint accelerations that provide end effector accelerations that we want. How do we find joint velocities that provide end effector velocities that we want? Okay, so we were interested in trying to somehow find velocities and accelerations that produce velocities and accelerations in the Cartesian space. Well, instead here, I'm asking you how to provide positions, how to find positions. And you would think maybe this is exactly the same, but no, this is not the same. This is a non-linear problem. This is a non-linear problem. It involves usually trig functions and something, some other stuff. So you can imagine I'm asking you L cosine phi equals to 5. How do you find the solution? Well, you can say arc cosine of 5 divided by whatever it was, right? But what if I have like sine phi times cosine alpha plus sine alpha cosine phi and so on? You already understand. You have to do trig identities and so on. Somehow it is not a matter of direct solution. And in practice, often enough, those expressions are so complicated that it's hard to solve them analytically. For some robots, like for KUKA robot, for example, I'm using KUKA to just mean like any robot arm, like FANUC, universal robot, etc. There sometimes exists a analytical solution. In fact, those robots, as far as I know, are designed to allow analytical solution. This has to do with how the axes are oriented and so on. But for them, you can find analytical solution. But in general, for general types of robots, it might be difficult. If you want analytical solution for one of those robots, KUKA, they are in scientific literature. I'm not sure if we want to spend time studying it. The way you often arrive to those analytical solutions is you study the, let's say, orientation matrix of the end effector or position matrix of the end effector. And you just say, at the same time usually, and you just say, okay, we have 6 equations, 6 unknowns. Let me try to solve all of them. They are trig equations, but you can use trig identity to solve them. All right, that is great. But today I want to show you general methods. In general, analytical solutions sometimes are not applicable, not easy to use, and so on. Okay, and also notice if you install a different gripper, you would have to rederive your analytical solution. So if somehow the length of your robot became bigger. All right. So our approach will be to linearize this expression and find solution via iterations. This is very typical situation. So that's what we are going to try to do. Okay. So first, the simplest possible case. So let's say we have exact solution to our problem. So we already know the solution. Doesn't get any simpler than that, right? We already know the solution. And we know joint velocities. What we will try to find is a solution in the next moment of time. So we already know our current solution, but we are moving on. So the robot continues to move. So I want to find inverse kinematics solution for the next moment of time. Okay. So what we can do here is to say, okay, the difference between next solution and current solution divided by the time that passes should probably be approximately equal to the joint velocities, right? To the joint velocities. So we can say from this expression here that next solution is probably approximately equal to the previous solution plus joint velocities times delta t. 29 is a profound formula explained to you Euler method for 101st time in your career, but it is useful to remember. How do we integrate differential equations? Well, see, it pops up everywhere, even in inverse kinematics. It's quite good. Of course, q dot 0, I didn't write it here, but q dot 0, let me say, oh, 1 second, can be found by pinf of g times v, right? That's how we found it. So if that is how we found it, then q1 would be equal to q0 plus pinf of g, right, times v times delta t. So if you want to somehow connect this to your Cartesian velocities, here you get the connection. You get Cartesian velocities here and delta t here. You have this situation. If you want to be a little bit sly about it, and I mean it in a good humored way, you could say, let me define dr as equal to v times dt, right? And then with dr, you can say, okay, now q1 is equal to q0 plus pinf j, right? Pinf j times dr, right? There was a plus here, not multiplication, of course. There's a plus. And if you divide, even define like delta q as q1 minus q0, then it becomes even more cute. It becomes like dq equal to pinf of j times dr. And you can see we are slowly approaching the definition of what j is. J, next we will say pinf of j is somehow like dq dr. if we move it around, we say J is dr dq, right? So what I'm trying to say is that if we play with this definition, we get all kinds of completely obvious things, right? This was just from Euler integration, right? So clearly, but then we could try to introduce notations that would make it a little bit more interesting. And then we get this guy that kind of looks like a definition of what Jacobian is, but upside down. And if we rearrange it, we can say dq/dr is equal to p of j, or dr dq is equal to j. All of this is good, but it's so it's nice that we get all results that kind of make sense. But at the end of the day, we're going to use this. So what you're going to write in your code is q1 is equal to previous q plus pseudo inverse of j times velocity of your end effector times delta t. If you want to do this kind of strategy where you know exact solution now, you want to update it next moment of time, okay? But you see, this is all kind of obvious. Like it follows from fundamental ideas of what derivative is. Okay. But what if you don't know Q0? That is actually very possible. What if you don't know what Q0 is? Well, if you don't know what Q0 is, what happens is you have to, you cannot rely on local linearization. What we did before is actually we relied on local linearization. That's how we were able to solve it in one go. Now we have to solve the problem R of Q is equal to R star. So let's just dive in and try to solve it. So first we define discrepancy. So the error or residual, something like this. Error or residual, something like this. Okay. So discrepancy between what RK is now as opposed to what is supposed to be. So this is now, that is what is supposed to be. Okay. We define cost function. Cost function is what we are going to minimize. It is E times E. So E squared, I could have said, but as a vector, so you have to be explicit how you square it. So we can also define initial position, K0, as RK at the point Q0. Okay. We can define initial discrepancy as E0, which is the difference between desired position and initial position. And we can finally define displacement. That is the difference between the solution and initial guess. So Q0 is again initial guess, initial position. So initial guess. K0 is initial position. E0 is initial discrepancy. Now we want to produce Taylor expansion of the cost function. Taylor expansion, I hope you remember how it's done. First, you get your original function evaluated at the point. Okay, so our function, let me clear everything. So our function is here. We evaluate it at a point E0. So our expansion will be at the point Q0. So at the point E0, at the point RK0, right? So we evaluate the original function. Then we take a derivative of this function at the same point. So again, we have JK is Jacobian. Of course, it is found again at the point Q0. Here, how do you read this thing? So let me show you. So this part here is a derivative of E to the right. This part here is e to the left. So remember, how do we take a derivative of a product? Derivative of the left on the left times the function on the right, plus derivative of a function of the right times the function on the left. So in this case, it will be e dot plus e dot e. Okay, so this is e dot. Okay. Okay. Now we evaluate e, of course, at the point e0. J always will be evaluated at the point e0, and we multiply it. We multiply this. So we evaluate it, you can say, at the point q minus q0, right? Q minus q0. Evaluate at the point q minus q0. Right. If you want to discuss this, I will leave it for a little bit onward. Yeah. I mean, I think it is reasonable to ask here why is this expression here, right? And this is a little bit hard because we skip so many steps. But in Taylor expansion, you remember the formula is like this. You say evaluate the original function, then take the derivative of this function and multiply it by x minus x0, where x is a variable, x0 is a point at which you evaluate the function. So delta here is x minus x0. So here is q minus q0. So this part here comes from the fact that we use a Taylor expansion, which is designed like this. You say it is a variable minus the value of the variable at the point of evaluation. And this is a derivative. Okay. So this is where it comes from. This is a derivative. This comes from Taylor expansion. Okay, this is the same thing, but in other direction. So again, derivative, variable of the Taylor expansion. Okay, so this was the constant term. Those are linear terms. Next, we'll get the quadratic term. Okay, so this is a quadratic term. This is the second derivative of f, and it is multiplied on the left, on the right by q minus q0. Again, if you don't remember Taylor expansion, you can look it up in multivariable calculus. You need the multivariable Taylor expansion, not the single variable one. They are equivalent, of course, but you know, you would find it easier to look at the multivariable one. Okay, so this is 31, expression 31. I'm not sure if it was clean. Preparing for this lecture, I tried it like 5 different ways to make it clean and not take like 30 pages. That was my best attempt. So sorry if I managed worse. Okay, now what we want to do is to take a derivative of f with respect to q and set it to 0. Set it to 0. Here, I can argue that this is the same as taking derivative with respect to delta and setting it to 0. I think that is a reasonable argument. I think that's a reasonable argument. But we can just verify it later. Like take derivative with respect to q, set it to 0, take derivative with respect to delta, set it to 0, see if the result is the same. All right, because the difference between q and delta is just this constant term. All right, all right. Now we take a derivative with respect to delta. And this is a familiar territory. This is something that we did today twice and the last lecture once. So this part goes away. We get those two guys become after differentiation this y e transpose j. Well, because those two guys are both scalars, so I can transpose one of them. So in this case, I transposed this guy. Transpose of a scalar is the original scalar. So this is how we get this guy here. And this guy is quadratic function. That's why we get 2 here. Okay. So we get 2E0 transpose JK plus 2 delta JK equals to 0. From that, we can find delta, and we can find it as JK inverse times this thing. Of course, before we can do that, we have to transpose both of those parts. So when we transpose both of them, E will no longer be transposed, J will become transposed, this will stay the same because it's symmetric, Q will become like go to the right, and we get rid of 2's. Yeah, this is standard procedure. We did it exactly the same way yesterday and today with N. All right, so the answer is this, right? We get J minus 1, J transpose E0. Okay, now remember we did a bunch of substitutions. So this guy here is a substitution for this thing. And this guy here, E0, is a substitution for RK0 minus RK star. Okay. Those were substitutions. So we put this to the right, and we get Q is equal to Q0 plus pseudo inverse of JK times the distance from the initial position of the point RK, the point K, minus desired position of the point K. Okay. Did we wait? I think we forgot the 1 0. No? Yeah, here we forgot a 0. Sorry, I apologize. So let me just correct it here, and we'll correct it on the slides before we publish them. So here we'll have a 0. Right here we have a 0. So unless I miss something, here we have a 0 too. So here we would have a 0 as well. Yep. Okay, that sounds correct to me, but I'm not sure. All right, and this expression, what it will get is put us a little bit closer towards RK star. What we can do then, after we are not going to land on RK star, because this is a linearization. Taylor expansion in this case also gave us linearization. So what we can do next is we can say, okay, we landed a little bit closer. Now we linearize again in this new point, and we repeat the same procedure. We don't have to derive it again. We just use this formula, right? We just say, okay, first we update our Q as Q0 minus J pseudo inverse RK minus RK star. Next time we update RK0 and Q0, and we repeat JK also updated. We repeat, we again get new Q0 minus new J pseudo inverse times new RK0 minus RK star. And we repeat it like 5, 6, 7 times, and we get close enough to RK, and we stop. The condition for stopping is very simple here. We can say when this discrepancy here is small enough, then we stop. If we are within 1 millimeter, we can stop. If we are within 2 millimeters, we can stop. This kind of stuff. So we can just directly use how close we are to the solution to decide if we want to stop or not. Okay. All right. So this is the way to solve this type of problems. Do we have questions? this is theoretically the most difficult part about inverse kinematics. If you look at modern papers, a lot of them have been on this exact topic, as in like how to make it faster, how to make it more efficient, what is best gradient-based methods, some other methods. Can we do it analytically? Can we do it symbolically, numerically, etc.? So this is the meat and potatoes of the field. Those inverse kinematics procedures. And what you're going to implement in your robots often would have to do with these things. Like with the inverse velocity problem, the question is just how to make it efficient enough. As in, you don't want to make a mistake of computing something twice, but that is, easy enough. With this, often enough what you do is you find third-party library. I think MoveIt is a ROS library, I'm not sure. But you have plenty of those. Those libraries will compute inverse kinematics for you. So this is the most important part here. Do you have any questions? Okay. Now, there are just a few more things I want to show you, and then we can conclude. So we don't have to just solve kinematics. We can also use our knowledge to check the solutions that we obtained or someone else obtained. Let's say someone gives us solutions like a software package. We want to check how good they are. So for example, how can we, and also even before going to the software package, we also want to check whether or not what we ask is even feasible. Is even feasible. I'll just give you examples. I'm not giving you exhaustive list of what you can do. I just want to direct your mind into the direction where you can go. So how can we check that velocity v sub k can be achieved? So you ask your solver to produce your velocities that you want. How can you check that this what you ask is even feasible? Maybe you're asking for too much, right? Maybe what you're asking is impossible. So how can you check that what you ask is actually feasible? Given our standard velocity problem, Vk is equal to Jk q dot. Well, if Vk lies in the column space of Jk, remember last lecture again, column space, right? Then it is achievable. If it lies in the column space, we can find, that is by definition what column space is, space of all achievable VKs, all right? So if it lies in the column space, it is achievable. How do we check that it lies in the column space? Well, we check that it has zero projection onto left null space. So zero projection onto the orthogonal complement of the column space. There is a projector to the column space. We have seen it today, I think, once or twice. Twice, I think. So I minus this guy will be projector onto the left null space, to the orthogonal complement of the column space. Okay. So we project V to the orthogonal complement of the column space, and we require that this is equal to 0. That is a check. So we want to check if K can be achieved. This is how. This is how. Easy, right? It's not very difficult. And this, your pin for JK, you probably already have it somewhere. So this check is not even computationally expensive. Next. Next. How can we check that the solution Q dot is minimum norm, given the problem Vk equals to Jk Q dot? How can we check the solution is minimum norm? Well, minimum norm solutions tend to lie in the row space. In fact, they all do. All minimum norm solutions lie in the row space. That is the definition of what row space is, the space of minimum norm solutions. So we need to check that it lies in the row space of Jk. How do we check that it lies in the row space of Jk? Well, same as before. We check that the projection onto the orthogonal complement of row space is 0. What is the orthogonal complement of the row space? Well, it is null space. And here is a projector to the row space. Here is a projector to the null space, right? So we just check that the projector to the null space is equal to 0. That's what we do. We require that the projection of Q dot to the null space of this Jacobian is 0. You can imagine we can make a ton of other checks that have something to do with projections. I think that is good for today. We have seen enough of those. Do we have questions about those last two? Well, if not, we'll finish with that. Next time, I think I'll look at the plan, but I think we will talk about hierarchy of tasks. And then we'll try to see if we can solve 2 tasks at the same time. Today, you remember, we were asking about velocities. What if we have angular velocities? What if we want to, at the same time, find a linear velocity and angular velocity? What if we have 2 arms and we want to, at the same time, solve it for 2 arms? What if we have priorities? What if we want to solve for our linear velocity? But if we can, we would also like to solve for angular velocity. But if we cannot, we don't have to. What if we approach singularity and we know that we no longer can solve for both, let's say, position and orientation, or velocities and position orientation? Can we somehow solve at least one of them, right? And leave the other one to do the best it can? Those questions we'll consider next time, unless I'm mistaken the plan, and then it will be like a week later. But I think next time. All right. Thank you, everyone who found time to join. And, see you next week.